Okay, let's begin here. So today we'll finish up this nearest neighbor classification. We'll start also talking about logistic regression. Of course, project number 3 is due next Tuesday at 5 p.m. Are there any questions before we get going here? Okay. So let's just briefly review nearest neighbor classification. And I think this plot that was on page 1 of my notes really helps illustrate what's going on. Just to review, let's say we have two variables, x1 and x2, and we're interested in figuring out or predicting which group, 1, 2, or 3, that this red dot should belong to. And if we say that we want to use k equal 1 nearest neighbor, what we do is we look at see, well, which of these observations is closest to the red dot. And we can see that we do have one observation, and it happens to come from group number 1, that is the closest. And so therefore we say this red dot is predicted to be from group 1. If instead we had k equal 3 nearest neighbors, we would go with group 2, because 2 out of the 3 are from group 2, 1 out of 3 is from group 1, and 0 out of 3 is from group 3. And so that's simply how it works. Now, what I just described to you is the process that the function knn.cv actually uses to make a prediction for the corresponding group, corresponding population. The CV corresponds to cross-validation, meaning if, let's say, this red dot was actually in my data set itself, it doesn't use the red dot to determine what the actual, it doesn't use the red dot in calculating the nearest neighbors. So essentially removes the red dot from the data set and then looks at the remaining k nearest neighbors. If instead we use the function knn, and this red dot was in my data set, and we were trying to classify or predict the observations in this data set itself, then whatever the particular group for that red dot, let's say it was 1, that would be factored into the k nearest neighbors. So if k is equal to 1, notice I will always have 100% correct classification rate. If k was equal to 2, I would also have k equal 1 as my prediction. If k was equal to 4, then I have a tie. And how does R break the tie? Does anyone remember? At random. Okay. Let's see here. Now, question then becomes, well, how do you choose k? And simply, the best approach is to try a number of different possible values of k. Obviously, you don't want to go too extreme in terms of what your k is, but start at, let's say, 1 and go up to, I don't know, maybe 10, see how it works. If you feel as though that, you're improving as you're going from, let's say, 7, 8, 9, up to 10, well, then keep on going to 11, 12, and so on. And whatever procedure gives you the best accuracy, and of course there's different ways to measure accuracy, the overall accuracy, or you could be looking at specific groupings in terms of its accuracy, use that to determine what the k is, choose the one that has the highest accuracy. And then lastly, whenever one does actually use k nearest neighbor in practice, generally speaking, you'll always use standardized data. Okay. So that takes us to where we left off then. We were talking about the place kicking example. And what we like to be able to do is predict the two groupings here. 1 is a success, 0 is a failure. We have standardized our data in terms of our training data set, and we've put that into an object called Z. We've also done this with the validation data set as well. We put it into an object called z.v. Now, do note that this validation data set, the way that I standardized it was I took the mean and the standard deviation from the training data set to standardize the validation data set. Okay. So, because there can be some randomness here in terms of how R actually implements it, and we want to be able to reproduce our results, I'm going to always set a C before I use the KNN or the KNN.CV functions. And so to use the KNN function for K nearest neighbor, the object train corresponds to my training data set, and that's equal to Z. And I'm going to use this validation data set, my holdout data set. I'm going to put that into the object test equal Z.V. So notice that we had used previously KNN to do resubstitution, but we're now using this now with a validation data set. So if I would have put Z into the test argument, which is what essentially we did before, then that would be fully resubstitution. But here, I have this separate data set that I want to try it out on. So that's why we're using KNN this way. Now, CL stands for classifications, meaning for your original training data set itself, what for each observation, was it a success? Was it a failure? In other words, the actual groupings. And that just so happens to be in the 9th column of place kick. I'm going to use K equal 1 nearest neighbors. Prob equal true gives me essentially the proportions for the observation, or the proportion for the observation corresponding to where it's classified into. In this case, since I have K equal 1, these proportions are all going to be equal to 1. Because it's always going to be 1 out of 1. Okay. Now, I put the results into NNC1 for the lack of a better name. Here are the first 6 predictions. So observation 1 is predicted to go into group 1, which means it's predicted to be a success. Then I'm going to also use the KNN.CV. So in this particular case, notice I don't actually have a test data set at all, because my training data set is, I'm trying to predict those particular observations. Just when I do that prediction, I remove the particular observation of interest out, and then I try to find the K equal 1 nearest neighbors from that. So train equals Z, classification, place kick 9th column, K equal 1, prob equal true, and we get exactly the same, at least for the first 6 observations, exactly the same predictions for these groupings. Okay. So now we can go back to what we learned in the discriminant analysis section, and we can use the summarize.class function to summarize how well this procedure worked. So to do this with the validation data set to begin with, then for my original here, for an argument, this is what I put in for the validation data set. Were they successes? Were they failures? What was actually observed? And that's the 9th column of my validation data set. And then I also, for classify, I put in, well, what does this procedure predict? And that's stored in this NNC1. What's returned to me is a list, where the first component here is what's called class.table. So the 17 here represents that 17 times the kick was actually a failure, and this nearest neighbor classification method got it right. But 21 times it was a failure and it got it wrong. It predicted it as a success. 229 times it was actually a success and it predicted correctly. But 15 times it predicted it incorrectly. So then if we look at the prop part of the list, this stands for proportion. So this 0.4474, and this is just review, is 17 over 17 plus 21. So it's looking at, for those that were failures, what's the proportion that it got right? So about 45%. 0.9385 is 229 over 229 plus 15. About 94% were right of the successes. The overall correct classification rate is 17 plus 229 over 17 plus 229 plus 21 plus 15. And so I got about 87% correct. Now, for the cross-validation, then we can do exactly the same thing. Original, I go back to my training data set, and I extract out the 9th column. Classify, where I save the results from using nearest neighbor classification. This is what I get. The overall correct classification rate is about 83%. This is a little bit unusual to have the cross-validation being less than what the validation is, but I think it's due to the fact that our data set is so heavily weighted in terms of the number of successes. I think that's probably why this happened. There's not a whole lot of really failures out there for the validation data set. Okay. Any questions? So that's K-1. Now I'd like to be able to repeat this process in an efficient way for K=2, 3, 4, and let's go all the way up to 10. And from that, we can make a decision about what should we use for K. So to do this, let me actually come on over here to 10. Excuse me. Let me make sure I have this read in, first of all. Good. Actually, let me do that too. Okay, so again, I want to set a seed to reproduce my results. Now, I'm going to be repeating this process for K=1 to 10, and I like to be able to save the results each time through a for loop when I'm doing this. And so I'm going to create a matrix called save.results, for the lack of a better name. I'm going to initialize it with NAs to begin with, meaning I'm just going to fill it with nothing. Essentially, I'm going to have 10 rows because I'm going to be looking at 10 different values of K. So each row is going to be corresponding to a K. I'm going to have 4 columns because what I'm going to do is for the first column, I'm going to put in K. The second column, I'm going to put in what's the proportion that I correctly predicted for the failures. Third column, same thing, but for the successes. And then last column is going to be my overall correct proportion. That's what save.results will be. This is with the validation data set. Save.results.cv will be from cross-validation. Okay, so then I write a for loop. We've seen for loops before. So I say for K in 1 to 10. Simply, this segment of code that's between the curly brackets is going to be executed for K=1. It's going to be done for K=2. And it's going to be done for K all the way up to K=10. And basically, the code here that's inside of here, at least this part, is essentially exactly the same as what we just saw before for just K=1. So NNC is going to get the results from using the KNN function. Notice I use test equals z.v. Notice also for the K argument, I put in this capital K because that's what my for loop is iterating over. I do a very similar thing for cross-validation. And then look at what I'm doing here. I'm going to use the summarize.class function to save the results. Just to show you how this works, how about I just put in here, oops, K=1. Let me also do that. So when I execute this segment of code all the way to saving the results from summarize.class. This is what I get. Look what's inside of what I get from summarize.class. Now, if I want to, I can pull out overall.correct by using that $ syntax. I can also pull out prop. Notice I get the proportions. But how about I just pull out the correct proportions? So there it is for the failures. There it is for the successes. These are the things that I want to save for each time that I run through this for loop. And so when I do this then, I'm going to combine together the value of k, the correct or the accuracy for the failures, the accuracy for the successes, and then the overall accuracy. I'm going to put that all combined together and put it into the kth row of my save.results matrix. So let's just actually do that. And if I execute that code, there you can see how it was entered in. Okay. I do the same thing for cross-validation. Now let me remove that here, and let's run the whole thing, and then print the results. And this is what we get. So we can see there's essentially about 60 different things that we want to look at here. In terms of, we have 60 different accuracies. That's a lot. So because of that then, how about we just simply do a plot of this? Rather than looking at, okay, k equals 5, what happened? K equals 6, what happened? And so on. And so in my notes, I have the plot, and we'll look at how I did the plot shortly. Actually, I do 2 plots. And I think this helps really summarize what's going on. So, on the y-axis, I have accuracy. On the x-axis, I have the value of k. Let's focus on just the validation data plot for now. Let me see if I can even make this a little bit bigger. That's too big. There we go. Okay. So first of all, let's look at the red line here. This corresponds to the failures. So we can see that as k is increasing, the proportion of failures that are correctly predicted goes down. Here's an intuitive reason for why this occurs. I think we only have about 30 or so failures in the data set. So as k gets up to 10, you're really looking for a large proportion of those failures to be in that nearest neighbor, in that neighborhood. So that's probably why that is happening. We can look at the correct successes, that proportion. Those are the blues. We can see that it kind of increases as a function of k. And then the black corresponds to the overall rate. And we can see that the black is remaining fairly constant, especially once you get above 2. So once you're at 3. And so from a plot like this, what you want to do is figure out what would be a good value of k. And let's say if we just focus on the black there, the correct overall. What would you pick for k? Probably 3. But you're really not losing much from 4, 5, 6, or so on. And so you can see how you can have more than one justifiable answer. Now, if someone said k equal 2 here, let's say you put k equal 2 on the test, I'd probably take off points. Because then you're essentially taking the worst case. Okay, that's not justifiable. Now, if we also try to factor in, let's say we want to try to get at those failures as well. Then it comes to a point where, okay, some of these larger values of k that for the overall rate seems to be good. Some of these larger values of k probably are not justifiable. I mean, we can see that 3 and 4 for the failures seems to do decent. So obviously this is the best. But this is the second best, this is the third best. And we can see overall, Here's the best right there for the correct for the overall rate. This is doing pretty good too. So if I'm really concerned about those failures, probably Kaggle 3, Kaggle 4 would be the best choices. Yeah.
Sorry, you said the reason that the overall correct failure is so low is like 40% accuracy. It's because of our data set. In other data sets, it should be higher. Yeah.
So you're saying, why are we even so low there?
Yeah.
The reason is it's just having a hard time predicting. So what I was saying before about this, why is this going down?
Yeah, because of the
It's because we have so few failures. That's why. But I didn't talk about at all, why is this just doing poorly there? And I think it's just simply because of the data. It's hard to predict. Distance itself is a very, very important variable. But the other variables are all, let's say, marginal in their importance.
And what was your reason for not choosing to put like incorrect failure and incorrect successful in this graph for choosing K?
Could you repeat your question, please?
What was your reason? Because you only added the correct prediction in the graph to choose K, what number of K you want to choose. Why you didn't put like incorrect prediction?
Oh, okay. Well, simply, what would be the incorrect prediction here? It's 1 minus whatever I have here. So if I put the correct, I get the incorrect. So I could have simply done this plot too with just doing incorrect only. But that's why. So, let's say though that we also had, let's say, more than 2 groups. Maybe we have 3 groups, 4 groups. You just do a very similar plot like this. Okay, you just add lines. Let's look at cross-validation. And we can see, once we get about up to, at least when we get up to 5, we're fairly constant for the overall. Maybe in the grand scheme of things, this 3 is not too different from when you have K equal 5 or K equal 6. Definitely, it would be hard for me to justify 1 and 2. And we can see a very similar thing happening here in terms of the correct failures and also the correct successes as well. So overall, the big picture here is that often more than one value of K is justifiable. And, you have to pick in the end, which is maybe most important, the overall rate or maybe the individual group accuracy rate as well. So how did I do this plot? Just use some methods that we've talked about before, maybe a few different new things. So first of all, I just wanted to make sure that I could get both plots on exactly the same graphics window. So I made an extra wide graphics window. So that's why I say dev.new, which opens up a new graphics window that's 10 inches. I don't remember off the top of my head if we've talked about this. Have we talked about this par function with respect to the MF row? We have? Okay. So what this is going to do, just to review, MF row stands for make frame by row, 1 row, 2 columns of plots in the exact same graphics window. Par stands for graphics parameters. Then I say plot. For my x-axis, here's where my K is. And we're doing the validation one first. It's the first column. For my y-axis, here is the, which one is it? This is the correct failure rate. I put some nice y-axis limits there, of course 0 to 1, that makes sense. I put some titles on the plot. This is one that we might not have talked about before. So there's a type argument in the plot function which controls, well, how exactly are you plotting everything? If I say type equal O, this corresponds to I want the plotting point and I want lines to join the plotting points. So that's why we see, again, these open circles with lines joining the open circles. I don't know why type equal O. What's the intuitive reason for using O there for that? Color equal red, x-axis label, y-axis label, and so on. Okay, so what this is going to give me is my red line that we saw on the plot. It's also going to set everything nicely up. It's going to put the grid lines on as well. How do I get those other lines? This is where I can use the function called points, where now I'm going to plot k on my x-axis, and on my y-axis, this is going to be the successes. Actually, I didn't need that y-axis limit. I do need, though, type equal O, plots the points, which makes sense for a points function, but also plots lines connecting everything. And then color equal blue. I do a similar thing for the overall correct classification rate, where I use black as the color. And then something I failed to mention. So AB line, I'm going to draw a horizontal line at 0.8546. This line that's produced is what we get from the best implementation of discriminant analysis. And so we can see here that this nearest neighbor classification overall seems to be doing very similar to discriminant analysis. Maybe slightly better on the validation data. But one reason why I wanted to include that there is because we talked about how discriminant analysis has some assumptions with it. For example, the multivariate normal. Or maybe an equal or unequal covariance matrix structure. Even with those assumptions, it's doing pretty good when we compare it to nearest neighbor classification, which essentially has no assumptions at all. And so that's, if you remember when we talked about discriminant analysis at the beginning, I say that this procedure is often referred to as being robust. The word robust in statistics means that the method works well, even if underlying mathematical assumptions are not satisfied. Regular old discriminant analysis is robust. So just to give you an idea, what do we do as statisticians in terms of research? Those are the kinds of things that we investigate. That's statistics research, to investigate how well does it do in those kinds of situations.
What did that value exact for 6? You didn't get that from the previous for loop, did you?
That is actually from the last set of discriminant analysis notes. So the dotted line it shows again what was the best overall rate from discriminant analysis from the last set of notes.
So if you want to get that for our own data set, you have to.
So I'm just going back to the last set of notes. I grabbed that value there and plotted it so that we can compare the different methods for prediction. And then lastly, of course, then I put a legend on my plot so we can differentiate everything. Okay. So, just like what we did with discriminant analysis, we'd like to be able to follow up with, well, where is it doing well? Where is it maybe having problems in terms of correctly predicting? So how about we take a closer look at k equal 4. And so I run some of the same kind of code that we just saw with the k, and while we could look at other values of k, I chose we're going to use k equal 4 here. We're going to look at it with respect to cross-validation. Later in my notes, I also have it for the validation data set. And so I'm just going to run the same kind of code as before, and this is what we get. Now do note that this C number is different than what would have been actually used in that for loop, and so that's why we see slightly different results, but it's very, very comparable. And so now with that then, what I want to do is look at principal component analysis. This will allow us to visualize this multi-dimensional data. And when I plot the corresponding scores, I'm going to have the plotting point corresponding to what was the prediction for the classification. And so this is what we get. The blacks are the failures, the reds are the predicted successes. And what we can see here, I think it's maybe best to compare to what we had before. So let me go there. So this is what we had before. Look at how it made those predictions. And we talked about with discriminant analysis often is just, if we just had the original data itself in terms of like x1, x2, we just simply are plotting lines to where divide everything here. And while that's not going to exactly happen with principal component analysis because we're not looking at the full information in the data, you would expect something like that to happen. And this is what we had. So look at where the black and the red are. Now compare that to what we now have for nearest neighbor. We don't have that big distinction here. And hopefully that makes some intuitive sense in terms of how nearest neighbor works. It's just looking, okay, let's look at, in this case, k equal 4 nearest neighbors. Let's look at all those other points that are nearby. And based upon that, we're going to make a prediction. And so this allows us then to have more flexibility. I mean, look at, we have like a black one right there, or a few blacks. And so this, excuse me, gives you some idea of how this is working. I mean, I think still overall, like what we had for discriminant analysis, we tend to have more blacks as PC number 1 increases. And that's because PC number 1 was really corresponding to the distance to the place kick. The larger PC number 1 is, the larger the distance to the place kick. And intuitively, if you're a football fan, you know the probability of success is going to go down the longer the kick is. And so you'd be more likely to predict a failure. And we see that kind of happening here. And you can look at all this in 3D as well. Let's see here. And you could also look at it for the validation. You can look at those on your own. Okay. Let's see here. I guess the last note then, well, how would you do variable selection here? Now, I've never seen anybody actually do variable selection with nearest neighbor classification. Some additional considerations. This first one we talked about essentially last time, but I want to just bring it up again. What if there are more than 2 populations and you're using the k&n function? Now, when you use the prob equal true argument value in using these functions, you are going to get the proportion, or what R is going to give back to you is the proportion of observations in your neighborhood that correspond to the actual predicted group. So if I have, let's say, groups 1, 2, and 3, and let's say the prediction was 2, what R will come back and tell me is that for, let's say, maybe for group 2 for observation 1, it was 0.4. It does not give you information about group 1 and group 3. Now you can see here with a value of 0.4 there, there's essentially 0.6 left over. And maybe 1 is actually 0.35 and 3 is, let's say, 0.25. And we can see that that's fairly close then for 1 and 2. But you don't have that information, unfortunately, from case nearest neighbor, from these functions. Maybe it might be nice to see that. Because this also leads you to think about, okay, where is this method having problems differentiating between the different groupings? But unfortunately, the functions don't give that to you automatically. Something else to think about. So with discriminant analysis, all we essentially needed were the estimated mean vectors for each group and the estimated covariance matrices for each group. And then we could just go ahead and throw away the training data. We didn't need anything else. Here, though, with k-nearest neighbor, you can never throw away your training data, because you always need that to determine what are the nearest neighbors to the observation I'm interested in classifying or predicting. So you can't ever throw that away. Now, an advantage of then discriminant analysis is that, again, once you have the mean vectors, once you have the covariance matrices, that's it. That's all you need. But let's say that you have a very large data set, and in an application of k-nearest neighbor, let's say if you have 1 million observations, well, you need to look at what the distance is between your observation of interest that you want to predict and the other 1 million observations. You need those distances. That's a lot. And let's say you have a lot of observations you want to predict. Well, you're going to be finding lots and lots of distances. So that is a disadvantage of using k-nearest neighbor. And once you get to very large data sets, computations can be perhaps kind of long. However, though, there are specific algorithms that have been developed to help with this process. And if you're interested in looking at that, you can take a look at the FNN package for an example of how this can be done. Now, something that we also kind of talked about before. If we go back to this original drawing here, oops. Let's say that we're using cross-validation for this red dot, and we're looking at the 3 nearest neighbors. Or actually, let's just do 2. We'll do 2 nearest neighbors. We can see the closest one is this one, the second closest is that one. Now, the way that R would approach this, using the function that we just saw, it would actually break the tie at random. But we can see that definitely observation 1 is closer to the red dot than observation 2. It would be nice if you could somehow take that into account. And there are different versions of k-nearest neighbor classification that actually do that. If you want to know more about that, here is a particular package. And lastly, you don't need to necessarily use Euclidean distance. There are many other distance measures out there as well. And here's a package that gives you some more freedom. So the purpose here was in this section was just to introduce you to k-nearest neighbor classification, introduce you to the way that is most often carried out. And also, though, if you're interested in this, here are some other options that are available to you. Okay? So that concludes in this section. Are there any questions? Okay. Let's now go to the next section. Logistic regression. This is a widely used statistical method. Now, with the word regression there, that means that we're going to be, estimating a regression model. And so it's going to have some similarities to what you would see like in a Stat 801 kind of course where you would actually estimate a regular old regression model. With a regular old regression model, you can predict the response variable or your dependent variable, depending upon whatever word you use in your previous work. You can predict that. But also, you can interpret the corresponding explanatory variables that are in your model. Excuse me. We haven't been able to do that yet with nearest neighbor or discriminant analysis. Now, the interpretation part, I'm only going to talk about very little because that's much more the focus of a course like categorical data analysis, which is a course that I teach here usually every spring semester, odd number years. It used to be every year in the spring, but we have a shortage of faculty, and unfortunately, we've had to cut back. And I think I've mentioned that I've actually written a book on categorical data analysis. I'm actually just about, in the next 1 or 2 months, I'm going to actually submit the second edition to the publisher. And so if you find it that you like this kind of stuff, dealing with logistic regression, please consider taking my categorical data analysis course. If you want to know more about it, there's my corresponding course website. Also, you'll see links to my book on from my website as well. So my purpose now is probably for the rest of today is just to give you enough background on logistic regression so that probably not until the next class period we will actually be able to use it for our main purpose of this section of the notes, which is to predict. Logistic regression is used just for 2 groups or 2 populations. So like the place kicking data, failure or success. After we do logistic regression, we'll look at something called multinomial regression, which will allow you to do 3, 4, or as many groups as you actually have. But for now, we're just focused on 2 groups. And so I'm going to give you just enough background on logistic regression so that we can actually do it for our main purpose in our class, which is prediction. Interpretation is, though, cover much more in a categorical data analysis course. So just to review regular old regression, so we can relate it to that, here's a regular old regression model. We have y as our dependent variable. The subscript r corresponds to the observation number. We have a linear combination of regression parameters denoted by the betas and independent variables, explanatory variables, covariates, whatever you want to call them, that are denoted by the x's. At the very end, we have an error term denoted by epsilon. What this error term is basically saying is that, okay, if I knew x1, if I knew x2, if I knew xp, I'm probably not going to still be able to perfectly predict what y is. So I'm going to have some error left over. We're just going to put all kinds of possible errors that can exist into something that we call epsilon, and we're going to say it's actually a random variable, where it comes from a normal distribution. The mean is 0, meaning on average your error is 0. But how much those errors deviate from 0 is dependent upon simply a variance, which we'll just simply call sigma squared. Also note that we have independence here, meaning that one observation essentially is not going to affect another observation. We have a capital N different observations. Now we could also look at the model like this, where we say, well, what would I expect y to be on average? And look what happens here. You still have this linear combination of the regression parameters with the x's, but now the error term disappears. Why? Well, because that mean was 0. I expect my error on average to be 0. This is important to understand, and this is something that you might not fully get in a Stat 801 course. It's important to understand that this, again, is what I expect y to be on average, which is different what y is, what truly is. Okay. Now, with this all set up here, basically, and this would be more fully discussed in like a Stat 880 course, a mathematical statistics course. Basically, because of this error term here, it has a normal distribution. This y then also has a normal distribution. And we can see, notice the way that we write it, the mean is that linear combination of the betas with the x's, and the variance ends up being just sigma squared. Now, with regression analysis, we're very concerned about what these betas are. Because notice if beta 1 was equal to 0, that means x1 essentially disappears from the model. There's no relationship between x1 and y. If beta 1 was greater than 0, that says we have a positive relationship, meaning as x goes up, y goes up. Negative, as x goes down, y goes down. What we saw from the matrix algebra part of the course is that we can put all this stuff into matrices. And so that to find the least squares estimates for the betas, let's say if I have all my betas into a vector called beta, the estimate of beta is called beta hat. All I need to do is take x prime x inverse, x prime y, and voila, we get our least squares estimates. Okay, now let's talk about logistic regression. Y here for us is now going to be binary. And simply we'll say it's either 0 or 1. Most often with logistic regression, people introduce this as 1 being a success, 0 being a failure, which obviously works well for the place kicking example because that matches that. And so since y is a binary variable, or a binary variable, it has then a Bernoulli distribution. So it's not a normal distribution anymore. Y is a Bernoulli distribution. You learned about that in like a Stat 801 kind of course where we were talking about the binomial distribution. Bernoulli corresponds to essentially where you have one trial. With the Bernoulli distribution, if you remember, there's simply just one parameter, pi, which is actually the probability of success parameter, the probability y is equal to 1. So the expected value of y then ends up being pi as well. The variance of y ends up being pi times 1 minus pi. Notice how I have r subscripts on those, because this indicates that every individual could have a different pi. And so our logistic regression model ends up being this. Remember how I had written a regular old regression model with expected value of y on the left-hand side? I can do the same thing now for a logistic regression model. Expected value of y sub r is equal to, well, just another notational thing, it's the pi, is equal to the exponential function raised to the linear combination of the betas times the x's, all that divided by 1 plus the exponential function evaluated at the linear combination of the betas times the x's. So if you haven't seen a logistic regression model before, this might kind of look weird. I was like, geez, that's kind of a weird transformation that we have here. Well, why is this transformation used? This pi has to be between 0 and 1 because it's a probability. Now, back in your algebra days, when you first learned about the exponential function, yes?
Pi is a possibility between 0 and 1. Y is equal to 0.
Sure. You know, in like a Stat 801 course, you talked about what the expected value of y was for a Bernoulli distribution. You know, how would you find that? Well, you would say, okay, let's see here. We'll write it out general form. Y equals 0 to 1. The probability mass function, in other words, pi times 1 minus pi. We have a y, we have a 1 minus y there, times the probability y is equal to little y. Does that look familiar? Okay. So if I put y equals 0 in there, look what happens. Pi raised to the 0, 1 minus pi raised to the 1 power, times the probability that y is equal to 0, which is 1 minus pi. Okay? And then plus pi raised to the 1 power times 1 minus pi raised to the 1 minus 1 power times the probability y is equal to 1. Okay, excuse me. I actually did this wrong. I was doing it's like, hey, this isn't working out. Sorry. That should be a y there. Notice that this here is the probability y is equal to either 0 or 1. So now when I do this, I get pi raised to the 0, 1 minus pi raised to the 1 minus 0 times y, which is 0, plus pi raised to the 1, 1 minus pi raised to the 1 minus 1 times y equal 1. And this ends up being pi. So the expected value of y for Bernoulli is simply pi. And so this is how I make that connection. Okay. Okay. So back what you learned in your algebra class when you first saw the exponential function. That's typically when it's introduced. The exponential function always gives you a positive value, no matter what. So e to the 0, e to the negative 1, e to the 1, you always will get a positive value. Now also notice here, look at the numerator, and notice how the numerator, that value, is essentially also in the denominator as well. So the numerator is always going to be less than what's in the denominator. And so because of that then, this can never, ever be greater than 1. And since the exponential function is always positive, it always has to be greater than 0. And so that's why we use this little mathematical transformation. There are other mathematical transformations that are used with respect to regression models when you have a binary response, but this is by far the most often used one. The main reason is because it can lead to some easier ways to interpret your independent variables. Okay. So we can also rewrite the model like this. So let me come back here. Notice how with my regular old regression model, I had this linear combination of the betas and the x's on the right-hand side. Could I somehow rewrite the model so that I still have that, and maybe the left side looks a little bit different? And yeah, you can. And it just uses some algebra, and you can rewrite your logistic regression model like this. So now I have the log of pi divided by 1 minus pi is equal to now the linear combination of the betas and the x's. On your own, you should make sure you can verify that. It's just using algebra and properties of logarithms. Now this is just notational. People will often take this stuff that's on this left side and they'll say instead, this is actually, we'll call it the logit transformation of pi. So they'll say logit of pi. So this is just a mathematical function, just like a shortcut expression for log of pi over 1 minus pi. Without getting all the reasons why people do that, there's also a type of model out there used for binary responses called a probit model, where probit stands for probability unit. Those kinds of models were actually developed first a long, long time ago. And eventually, once people start using logistic regression more so, people say, okay, well, if I have something called probit, how about we call this logit? And so that's how it came about. And so there are two different ways then that we will express our model. You don't need to always put the R there. If it's clear that, okay, yes, I am going to be doing this for every observation in my data set, and so I just drop the R there. But these are the two different ways that we'll be able to write out our model. Now, this kind of model has, I don't want to get into this too much, but I think it's helpful to understand this. Remember how with a regression model, you're often focused on these regression parameters. If beta 1 was equal to 0, that says, well, x1 has no relationship with the response variable, the dependent variable. Notice how the same thing happens here if beta 1 was equal to 0. If beta 1 was positive, this says that as x goes up, the probability of success goes up, or pi goes up. If beta 1 was negative, then it says as x goes up, probability of success goes down. Okay? Now you can actually see this then in a plot. So this is actually from my book. I have a function in my book called piplot.r, but I have it available on our website too. And let's say we have just a simple logistic regression model where we have just one independent variable, x1. And we're going to set beta 0 to equal to 1, and then first we're going to set beta 1 equal to 0.5. Look at the plot on the left. I have x1 here. I have that pi, probability of success, on the y-axis. And so that we can see that as x is increasing, notice how the probability of success is going up. Also look at the shape of the line there. So just to emphasize, what am I plotting here? I am plotting e raised to the 1 plus 0.5 times x1 over 1 plus e raised to the 1 plus 0.5 times x1. That's what I'm plotting on the y-axis. Notice how the function itself looks, I'm sorry, the line on the graph looks kind of like an S almost. Also notice it has a symmetry property with it. It's called rotational symmetric. Or if I were to try to draw a straight line at pi equal 0.5 there, you can see that if I were to take the top, stuff that's above that pi equal 0.5 line, I could rotate it down and get exactly what I have down below. When beta 1 is negative, well, look what I get. As x goes up, probability of success goes down. Okay. How did I do a plot like this? Well, I can just simply use the curve function that we've seen before. And I can say curve for the EXPR argument, which means expression. What's my mathematical expression? I just simply put in what that logistic regression model would be, where I've set what beta 0 is, what beta 1 is. And if you remember with this function, no matter what you are actually plotting it as a function of, you always have to put x in there, because that's what's on the x-axis. So I can't put like x1 there. It has to be just x. Then I do some more fancier things in terms to get the notation, the Greek letters and stuff on there. You're welcome to take a look at how I did that. You're not responsible for that. But the expression function itself in R allows you to do fancy Greek or fancy mathematical characters on a plot. Okay. Some questions. Come back up here to the plot. So let's say that, so beta 1 here was 0.5. What if I increase beta 1 to like 1, 2? What do you think will be the effect on this plot? Yeah, so my slope is higher essentially. And so, maybe I might have something that looks like this instead. Woo! Well, that wasn't the best. This would not go down like that. But, I'm going up faster, okay? If, let's say beta 1 was, let's say, more negative, let's say negative 1, then I would go down quicker. If beta 1 gets closer to 0, essentially, this is going to be more elongated, this curve that we see there. What would a plot of the logit of pi versus x look like? So here's, let's say, x1. Here's the logit of pi. Let's say beta 1 is 0.5. So this is what it would look like. Yeah, it's just going to be a straight line. Okay? Okay, so how do we go about estimating these regression parameters, the betas? Well, we use maximum likelihood estimation. So if you remember that brief introduction to maximum likelihood estimation before, we actually looked at a Bernoulli distribution in that particular situation, and we wrote out a likelihood function. We talked about how you would find the maximum likelihood estimates for pi. Well, this is the direct extension to this. So here's my likelihood function, but now I have potentially n different pi's to worry about. Or before I had just one pi. But the key is that this is going to remain exactly the same. I just simply write out probability y1 is either equal to 0 or 1 times the probability y2 is equal to 0 or 1. I can condense this using product notation, and this is what I get. So product of a whole bunch of Bernoulli distributions, n of them. What we had previously in the maximum likelihood estimation notes was exactly the same thing, except for we did not have an R on the pi because we only had one pi. That's the only difference. But how we are actually getting these different values of pi corresponds to our logistic regression model. So in fact, this likelihood function actually could be written out with that expression for our logistic regression model in there for wherever we see a pi sub r. You can see how that gets a lot more messier. And so now my likelihood function is actually written, since now I don't have pi parameters anymore, I have these beta parameters. So now my function is this: the likelihood of beta 0 through beta n given my observed dependent values that came about. So now instead of having n parameters, I have p plus 1. So similar to what we did previously, we would take the log of the likelihood function. The expression is just going to become much messier because we have these betas to worry about. And so I'm not going to ask you to do this derivation on a test or a project, but this is what the log likelihood function essentially simplifies down to. So what would I want to do next? Take the derivative with respect to beta 0, set it equal to 0. Then also take the derivative with respect to beta 1, set it equal to 0. Do that all the way down to beta p. And so now I have p plus 1 equations and p plus 1 unknowns. And I need to solve for what those betas would be. Except in the most simple situations, there's not a closed form expression. So I can't say beta 0 is equal to, let's say, the sum of the y's times the x's. I can't say that. Unlike what you could do with the least squares method, with regular old regression analysis. So instead, because of that, I'm going to need to use what are known as numerical iterative procedures to try to, for every single data set, find what values of the betas actually maximize this log likelihood function. And depending upon your background, you may or may not have seen these numerical iterative procedures before. So let me just briefly mention what's going to happen here. Imagine a scenario where I somehow come up with some initial estimates for these betas. And since these are initial estimates, I'm going to put a superscript 0 up there. Say, hey, this is like stage 0 or step 0. How could I come up with these? Well, how about if we just use regular old regression analysis? Even though the assumptions would be wrong, I could use that to come up with an initial set of betas. Then I'm going to apply a particular method that allows me to come up with a new set of estimates. Let's call them exactly the same thing, but now since this is, let's say, step 1, I'm going to put a superscript 1 there. And so what happens then next is that I'm going to compare these two sets of estimates. If these estimates are very, very, very similar to one another, I'm done. I have found what these actual beta hats are. If they are not similar, then I'm going to go to a new step. Go to step 2. Where, and I didn't say this as well as I should have, where to find these new ones, I'm going to, without getting all the details, use a particular algorithm that will hopefully maximize or get me closer to the maximum of that log likelihood function. So I get these new estimates and I'm going to compare at step 1 and step 2. If they're very similar to one another, I stopped. Meaning that my log likelihood function is actually not actually improving really at all. I have found where the maximum is. And so therefore, I'm going to use those beta hats as my maximum likelihood estimates. If they're not similar, then I keep on going and going and going and going until I have maybe some predetermined maximum number of iterations. So that's what a numerical iterative procedure is actually trying to do. And that's what we have to use to find these maximum likelihood estimates. The actual numerical procedure that most software packages use for something like this is what's called iteratively reweighted least squares. I won't ask you questions about that. We just need to go over this so we get to a point where we can actually use these models. But just to give you a little bit of background, so you all know what least squares estimation is. If you've taken a full regression analysis course, you've heard of weighted least squares, where it's very similar to least squares, but now you're weighting each observation. The weight is typically done, corresponds to the an estimated covariance matrix for your response. Okay? And so that's what weighted least squares estimation is. Now, the reweight then comes about through, I'm going to, in the iterative part, is that I'm going to basically find new weights at each iteration or each step of this process. So that's where the name comes from. We have a particular function in R that will automatically do this for us. That's why I'm just kind of glossing over some of the exact details. In a course like Stat 821 or 822, you would actually be required to actually be able to program this yourself into a statistical software package to show that you can actually do this yourself rather than rely on routines that have already been developed. Okay. So this process is going to continue. At each step, your log likelihood function will continue to increase based upon how this algorithm is constructed. And eventually you get to a point where that log likelihood function is not going to increase anymore. And then also that means your betas are going to be about exactly the same. When that happens, then you have what's referred to as you've reached convergence. You have your sets of your betas, or your beta hats, are converging to what they should be in the end. Now, there will be times where, let's say you've set a maximum number of iterations of 20. And at iteration 20, that log likelihood function is still increasing. It's not being about the same. Your betas are still changing. When that happens, you have what's called non-convergence. Do you think you should use those estimates that you get if you reach iteration 20, you have not converged? The answer is no. Because iteration 21 will give you probably different betas, a different model, a different, in the end here, different prediction. And so you should not. At the end of the notes here, we will talk about one specific situation that does happen with logistic regression where this convergence is not possible. Usually when I teach a course like this, and if I allow students to use their own data for the course, usually I will have one or two groups have that happen to them where they don't have non-convergence. I'm sorry, where they do have non-convergence. Given how small our class is, I bet that won't happen, but it's very important for me to discuss, so we will talk about that at the end of this set of notes. Okay. So now we get to an example finally. Again, we're going to use the place-scaling data set here. And so the purpose here is simply to show how we can estimate this model. Eventually we'll get to the prediction part in terms of predict a success or failure. So the way that this model can be estimated in R is through a function called GLM. GLM stands for Generalized Linear Model. Why is it called that? Well, a logistic regression model is actually a special case of a class of family of models called generalized linear models. So that's where that comes about. If you take my categorical data analysis course, Stat 875, you will learn that. And so this is the model that we actually want to estimate. So I have my week variable in there, I have my distance variable in there, I have my wind variable in there, all the same variables that we've been using. So to do this estimation, I read in my data, and while we won't use it right now, I also read in my validation data set. So when I say I read in my data, this will actually be my training data. And to use this function, I'm going to save the results into an object called mod.fit for the lack of a better name, meaning model fit. I say GLM, then formula. This formula argument works the same way as it does with the LM function. So I say formula, my dependent variable, in this particular case would be good. It tells me, is it a success or is it a failure for that place case? Then tilde, and then I separate my independent variables by plus signs. I just simply write them all out. I specify where my training data is by just using the data argument. And then lastly, for the family argument, I need to tell R that I want a logistic regression model. And this then gets into understanding what generalized linear models are. If you remember, I said Y had a Bernoulli distribution for us. Well, of course, the generalization of Bernoulli is binomial. So that's why you see binomial here. Remember how we were linking the logit of pi to that linear combination of the betas and the x's by using the logit function, mathematical function. So that's why I say link equal logit. And so if I run the code and then just simply type mod.fit, I get all my beta hats. So here's beta hat 0, here's beta hat 1. So based upon that, I can write out my model, my estimated model like this. Notice I say logit of pi hat, because now this is my estimated model versus my true model. I say 4.78 plus, minus 0.0247 times week. And I can keep on going all the way down to the win variable, negative 0.63 times win. That's my estimated logistic regression model. Okay, we are basically running out of time here. But just to foreshadow what we'll be doing next time, we will use this model to come up with a pi hat. So for a particular value of week, particular value of win, particular value of distance, we can use this estimated model to come up with an estimated probability of success. So let's say that the estimated probability of success for a particular set of independent variables was 0.6. What do you think we should predict this observation to be? A success or failure? Well, success, because that 0.6 is greater than the probability of failure, which would be 0.4. But it's not that necessarily that simple. And this is actually one of the strengths of using logistic regression for this kind of stuff, is especially in situations where you're worried about making sure maybe you can predict the zero group really good. You don't have to use 0.5 essentially as that cutoff probability to say predict success or failure. You can make that cutoff probability 0.7 or something else. And we will look at a tool called receiver operating characteristic curves that help us make that decision. Okay, we are out of time, so let's take a look at what's next. Okay, so my usual office hours. We will continue with logistic regression on Thursday, and we'll probably even next week have to do some more logistic regression. Looking further ahead, though, again, project number 3 is due next Tuesday at 5 p.m. Depending upon how far we get in Thursday's class, will then correspond to what I tell you for project number 3 for that logistic regression part, how much of it you need to do. Do you need to do all of it? Or maybe, since we didn't get far enough, I will chop off some of the last parts of that logistic regression part. Also, something to take note of. Test number 3, Thursday, November 30th. Cluster analysis, discriminant analysis, nearest neighbor classification, and logistic regression. Those would be the topics of that test. I haven't made the test up yet, but I do know the topics. Any last questions? Okay, that's all for today then.